Hello everyone, welcome to Math 115 College Algebra. So this section, 2.4, is going to be on complex numbers. So I'll quickly kind of review like what an imaginary number is, what a complex number is, and then we'll talk about in particular how to add and subtract complex numbers, how to multiply and divide complex numbers, and then we'll look at a little bit of how to simplify if we have powers of something called I, which we'll review. Okay, so to motivate this, let's look at this. Let's look at a quadratic equation that we're trying to solve. Let's say we want to solve this quadratic equation, x squared minus 1 equals 0. Okay, from previous sections, we know how to do this, right? We can factor the left-hand side. This factors into x plus 1 times x minus 1, right? It's a difference of squares equals 0. So one possibility is x plus 1 equals 0. The other possibility is x minus 1 is equal to 0. In this left case, I can subtract 1 from both sides. So one solution would be x equals negative 1. And the other solution would be x equals positive 1. So we have two real solutions, right, to our quadratic equation. What if I change that quadratic equation slightly? What if I write it this way? X squared plus 1 is equal to 0. Well, now we have a problem, right? Is there something for which if I square and add 1, I can get 0? No, right? Another way of saying this, if I bring the 1 to the other side, I can write this as x squared equals negative 1, right? There's nothing that I can choose for x such that if I square, I get negative 1. At least there's no real solutions. So in this case, we'd say there's no real solutions. So how do we handle this? Because in general, whenever you have a quadratic equation like this, it turns out that in general, there should be two solutions. They may not be two real solutions, but there should be two solutions. So in this case, we are going to actually have two solutions. So you'll see in a minute, we have to basically define what we mean by the square root of negative 1. All right, and that will allow us to come up with two solutions. Okay, but it's correct that there's no real solutions. Okay, but there will be two solutions once we define what we mean by the square root of negative 1. And we'll see that in a little bit. Okay, so before I get there, let's just review how to simplify radical expressions, like just the square root of some particular number. So let's say I want to simplify the square root of 36. Well, 36 is a perfect square, right? It's 6 times 6. So one way of thinking about this is I can just write this as square root. This is really 6 times 6. So whenever I have a pair of things underneath the radical, it can come out as a single thing. So that's just equal to 6, right? The other way of doing this is you could factor 36 into a product of prime numbers, right? You could find the prime factorization. We could do the tree on it. So this is going to be 2 times 18, 2 times 9, and then 3 times 3. So then I have the square root of, remember 36 is really 2 times 2 times 3 times 3. And again, wherever I have a pair of things, so I have two 2's, it can come out as a single 2, right? It's like basically saying the square root of 4 is 2, right? So it comes out as a single 2. Or you could say the square root of 2 squared is just 2. And then the square root of 3 squared, so if I have a pair of 3's, it comes out as a single 3. You got to be a little careful. What do I have left behind? I always have a 1, right? Times 1 isn't going to change it. And the square root of 1 is equal to 1. So in this case, this is just going to be 2 times 3, which is 6, right? So we'll get the same answer, 6. So sometimes it's nice to just find the prime factorization and pull out pairs of things. So in the next one, if I have 27, right, I can factor, it's going to be 3 times 9, and then 3 times 3. So I have 3 times 3 times 3. So a pair of those 3's can come out front as a single 3. And then I can't do anything else with the other 3 that's underneath the radical, so I just have to leave it there. So square root of 27, or radical 27, is equal to 3 radical 3. Let me box the answers here. So this one's 3 radical 3. Here, I can factor the 50 into 2 times 25, and then 5 goes in 5 times, right? So then if I write that, it's 2 times 5 times 5. The pair of 5's comes out as a single 5, and I'm left with radical 2. So square root of 50 is 5 radical 2 when you simplify it. And then finally, square root of 32, if I factor 32, it's 2 times 16, 2 times 8, 2 times 4, and then 2 times 2. So now I have basically 5 2's, right? 2 to the 5th underneath. But then every pair of them comes out as a single 2. So I have 2 pairs. I can pull out 2 2's. And I'm still left with radical 2 inside. And then I can simplify this. 2 times 2 is 4, right? So this is going to be 4 radical 2. That would be the simplification of square root of 32. Okay. So now let's get back to our motivation up top. What happens if we take the square root of a negative number? What if we try to take the square root of a negative number? So I'll just start with the easiest case. Let's say I have square root of -1, and I want to find the answers to that. I'm going to call it like a. So what is a? So this means if I square a, whatever a is, if I square it, I have to get -1 as my answer, right? So if a equals the square root of -1, that's equivalent to saying a squared equals -1. But there are no real numbers. Let me write this out here. There are no real numbers squared that equal -1. So a can't be a real number. Right? There is no real number a such that if you square it, you're going to end up with -1, right? When we square something, we always get something that's non-negative. It could be 0 or it's going to be positive. It's always non-negative. Okay, so how do we handle this? Here's where we're going to define basically we're going to define a new number. It's called an imaginary number. So we're going to define square root of -1. We're going to give it a name. We're going to call it I. Okay, so it's just by definition, the square root of -1, we're going to call that I. And by doing that, we're going to find it super useful, okay? What does this mean? It also means if we square I, so if we square I, then that means I'm squaring square root of -1. What do I get back? I get back -1, right? This is going to be, so this is really I times I. So this is square root of -1 times square root of -1, which gives us -1. So another way, if you want, you can think of the definition this way. I squared is equal to -1. Okay, either way, either I equals the square root of -1 or I squared equals -1. So we're defining, it's called an imaginary number. All right, so how does it help us? Well, now let's look at some more simplifications of radicals here. So I'm going to simplify the square root of -81. So in general, there's no real number, right, that when squared will give me -81. But I can write this as, this is the square root of 81 times -1. And remember, we can always break this up into the square root of 81 times the square root of -1. Well, the square root of 81, you could do the tree if you want, but this is just going to end up being 9, right? Because it's a perfect square. So this is 9. And remember, we just defined what is the square root of -1? It's I. So this is going to be equal to 9i. So it does have an answer if we introduce these imaginary numbers here. Okay, what about square root of -24? First of all, let me factor 24 so we can simplify that piece. So this is 2 times 12, 2 times 6, 2 times 3. So this is like the square root of 2 times 2 times 2 times 3 times, and I still have a -1 in there, right? So I can pull out a single 2. I'm left with square root of 6 and then times square root of -1. But remember, square root of -1 is I. So this will be 2 radical 6 times I. Okay, what about square root of -45? So 45 factors into 3 times 15, 3 times 5. So this is really 3 times 3 times 5 times -1. So the 3's come out as a single 3. I still have a radical 5, and then the radical -1 is going to be my I. And then the last one, so this negative has to stay, right? This negative is on the outside. So negative square root. 16 is basically going to be 2 to the 4th power, right? It's 2 times 8, 2 times 4, 2 times 2. So it's 2 times 2 times 2 times 2 times -1. So the 2's come out as single 2's. And I have left square root of -1, but that's I, so this is going to be minus 4i. And that would be the result. Okay, so it's by definition, we're extending the set of numbers to now what's called the set of complex numbers, right? Including these imaginary numbers. So what is a complex number? Complex number is basically the sum of a real number and an imaginary number, and it has the form a plus bi, where a and b are real numbers. So a and b are real numbers. The a here is called the real part, right, of the imaginary number. And then the bi is the imaginary part. So a complex number consists of a real part plus an imaginary part. All right, so we're only going to do a little bit with complex numbers in this course, but one of the things we may want to do is we may want to add complex numbers together, right? So it's actually very straightforward. It's almost what you would think. So to add complex numbers together, I'll write it out here. So to add complex numbers, we first add the real parts. Then add the imaginary parts. And that's it. You can think of this as like combining like terms. We're combining the real numbers and then we're combining the imaginary numbers. Okay, so if I have this example where I have 3 minus 4i, and I want to add 2 plus 5i. What I do is I add the real parts. So the real parts are the 3 and the 2. So that gives me 5. And then I add the imaginary parts. Negative 4i plus 5i, that's going to be a positive, right? Negative 4 plus 5 is positive 1. So it's plus 1i, but then we never write the 1, right? I can just write this as 5 plus I. So that would be the sum of those two complex numbers. Okay. What about subtracting? I mean, subtracting is similar. In fact, we can think of subtraction as being a special case of addition, right? So now I want to subtract this complex number, 2 plus 5i, from this number, right? So in other words, I want to start with 3 minus 4i, and I want to subtract 2 plus 5i. That's what it means to subtract 2 plus 5i from 3 minus 4i. So what I would do is I would just convert it into an addition, right? So to subtract, we change, I'll say we will rewrite the problem as an addition problem. So rewrite it as an addition problem. So what does that mean? Well, remember in general, just with real numbers, right? If I have a minus b, this is really the same as a plus, right? I change my subtraction to an addition, and I can do that as long as I add, what am I adding? I'm adding the opposite of b now, right? So I'm adding the opposite. So subtraction is the same as adding the opposite. So in this case, I would take my first complex number, 3 minus 4i, and instead of subtracting, I'm going to add. Now the opposite of the second complex number basically means negative 1 times the second complex number. And to simplify that, you're going to basically distribute in the negative 1. It's basically going to change both of the signs, right? So this becomes 3 minus 4i, and this will become negative 2 minus 5i. Okay, and then we add the real parts and add the imaginary parts, right? Think of it, again, as combined like terms. So I'm going to add the real parts. 3 minus 2 is 1. And then I'm going to add the imaginary parts. Negative 4i minus 5i is negative 9i. So that would be my answer. All right, so subtraction is basically just an addition as long as you add the opposite of the second complex number, right? So you're going to basically distribute in. You're always going to distribute in a negative 1. It's going to change both of the signs of that second complex number. Okay. What about multiplying complex numbers? So let's start with a simple case. Let's say I want to multiply a complex number. So this complex number is 6 plus 2i. I want to multiply it by a real number, right? Just a 3 here. To do that, you can almost guess what you would think you would do. Just distribute in the 3, right? So if I distribute in that 3, I have 3 times 6. That's going to be 18. And then 3 times 2i is going to give me 6i. And that's it. That's my answer. Okay, so it's easy if you multiply by just a real number, right? Just distribute in the real number. Same thing here, right? So if I distribute in the 1/2 here, this is going to be 5 halves, right? 1/2 times 5 is 5 halves. And then 1/2 times minus 2i, I'll do over here, 1/2 times minus 2i. You can think of it as over 1 if you want. The 2's cancel, and I just end up with a negative I. right, over 1, which is negative I. So this is going to be 5/2 minus I. So that would be the answer. Okay, what if we want to multiply? So that was just a real number times a complex number, right? What if now we want to multiply two complex numbers together? Basically, we can do this by foiling, right? It's similar to foiling because it's 2 terms times 2 terms. The only thing you have to be careful with, and this is like a really key point here, right? So we can foil like we normally would, right? Multiplying the first, outer, inner, last. But the key thing is, remember, whenever we end up with an I squared, that's equal to -1 by definition. Okay? And then we can combine like terms, right? We can group together the real terms, imaginary terms, and that will give us the answer. So let's try this. So I want to multiply 3 minus 4i times 2 plus 3i. So I'm going to multiply the first terms. Let me just write this out again. So first times first, right? That's going to be a 6. Outer, 3 times positive 3i. Well, that's going to be a 9i. Inner, negative 4i times 2. Well, that's going to be a negative 8i. And then last, I have negative 4i times positive 3i. Well, negative 4 times positive 3 is negative 12. And then I times I is I squared. Okay? But here is where you have to be careful. This I squared is really a -1. So I have 6 plus 9i minus 8i. And then what's negative 12 times -1? Right? This is really multiplying now, right? Negative 12 times -1 is a positive 12. Right? Because I have the I squared there, which is -1, it changes the sign to a positive 12. And now I combine like terms, right? So I add the real parts. That's going to give me 18. And then I add the imaginary parts, 9i minus 8i. That's, I guess, plus 1i, which is just I. So plus I. And that is my answer. Right? So when I multiply these two things together, these two complex numbers, I'm going to get 18 plus I. Okay, let's do this one. So we're going to multiply those two complex numbers together, right? So I have 1 minus 2i times 1 plus 2i. So 1 times 1 is 1. 1 times 2i is positive 2i. Negative 2i times 1 is minus 2i. And then negative 2i times positive 2i, well, negative 2 times positive 2 is negative 4, and then I times I is I squared. And again, remember that this is going to be, the I squared there is going to be a -1, right? So this becomes 1 plus 2i minus 2i, and then negative 4 times -1 is plus 4. And notice what happens in this case, right? So the 2i and negative 2i, the imaginary parts, cancel, right? They give you 0. And then I just have 1 plus 4. I just have a real number answer, right? It's just positive 5 is my answer here. Why did this happen? Because these two complex numbers are kind of special. So this is just 5. It's just the final result is just a real number 5. So it turns out in this case, these two complex numbers are what are called complex conjugates of one another. So these two right here are complex conjugates of one another. All right, what does that mean? Well, if I have a real number, I'll just do this in general. Let's say I have A plus BI. Its complex conjugate is if I change the sign of the imaginary part. So if I multiply by a minus bi. So this number is the complex conjugate of that number. And vice versa. This is the complex conjugate of this number, right? They're the same, except on the imaginary part, the signs are different. The signs are changed. And notice what happens if I multiply these two together, right? So I'm multiplying a number by its complex conjugate. I'm going to get a times a, which is a squared, a times negative bi, which is minus abi. Then I have positive bi times a, which is positive, and it doesn't matter the order, right? It's positive abi. And then bi times negative bi, which is negative b squared I squared. But this, remember, I squared is negative 1. So the imaginary terms cancel, and I'm going to get a squared, and then minus b squared times negative 1 is plus b squared. See how I always get a real number here? This is going to be a real positive number. Okay, why did I spend all this time talking about multiplying a complex number by its complex conjugate? Because this is what we need when we want to divide complex numbers. So, basically, when you divide complex numbers, the rule is, like the math etiquette, some people will say, is that there should be no imaginary numbers, no i's in the denominator. They should just be in the numerator. So how do we get rid of them? Well, we know that if we multiply, and we just saw that here, right? If we multiply a complex number by its conjugate, we're going to get rid of all the i's, right? We just get a real number. In general, we're going to get a squared plus b squared, right? There's no i's in here in the answer. So that's going to help us to divide complex numbers where we're going to end up with no i's in the denominator. All right. First, let me make sure that we totally understand complex conjugates, right? So I'll make a little list here. Let's say this is the original number. And I want to write its complex conjugate. Let's say the original number is 1 minus 2i. Well, remember, the complex conjugate is going to look exactly the same, except you're going to change the sign of the imaginary part. So the conjugate in this case will be 1 plus 2i. Right? If the original number is 1 minus 2i, the conjugate is 1 plus 2i. Let's say the original complex number was 3 plus 4i. Then the complex conjugate would be 3 minus 4i. I'm just changing the sign on the imaginary number, not on the real number, right? The real number stays the same. What if it were negative 7i was my original complex number? Remember, this is really the same as like 0 plus negative 7i, right? There's no real part in this case. So the answer will be 0. That's not going to change anything. And then I need to change the sign on the imaginary part, so it'll be plus 7i. Okay, in general, if it were a plus bi, then the conjugate would be a minus bi. Okay, and that's the example we did up here, right? Where we multiplied it and we got a real number. And I guess this is also true, right? What if the b is 0? What if you just have a real number? What is the complex conjugate? It's the same real number, right? Because there is no imaginary part, so there's nothing to change the sign on. It's just the same real number. So like if you had, if my original number was 3, my complex conjugate would also be 3. Okay, so let's do a quick example with that then. So if my original complex number is 2 plus I, what's the complex conjugate? Well, it'll be 2 minus I. what if the original number is negative 2i? Again, maybe you can think of this as minus, and this is negative, like 1/2 I. So the conjugate is going to be 0 plus. I change the sign on the imaginary part. And then I don't need to write the 0, so I can just write it as 1/2 I. And then if my original number is negative 5i minus 7, first of all, you should probably write the real part first. So negative 5 minus 5i, that's how we usually see it. The real number stays the same, and I change the sign on the imaginary part. So it'll be negative 7 plus 5i. Okay, so why is that going to be useful for dividing complex numbers? Well, we can divide complex numbers by multiplying the numerator and denominator by the complex conjugate of the denominator, because that will eliminate all the i's from the denominator. So here, I'm going to write that out here. So let me make some more room. Let's say I want to divide these two complex numbers, right? So 2 plus 5i divided by 4 minus I. So the rule is to divide complex numbers we multiply the numerator. So the numerator, let me fix that. And denominator by the complex conjugate of the denominator. Complex conjugate of the denominator. And that will eliminate all the i's from the denominator. And why am I able to do this? Because I'm really just multiplying by a factor of 1, right? I'm not changing it, I'm just rewriting it. So here, we'll see how this works by example. So I start with 2 plus 5i divided by 4 minus I. And I'll put these in parentheses. I want to multiply the numerator and denominator by the complex conjugate of the denominator. So the denominator is 4 minus I. What's the complex conjugate of that? It's going to be 4 plus I. Right? Remember, I changed the sign of the imaginary part. And I want the same thing in the numerator, 4 plus I. See how this is a factor of 1? So this is a factor of 1. So basically, I'm multiplying this. Basically, I'm dividing these complex numbers, right? But if I multiply by this factor of 1 here, I'm not changing this. I'm just rewriting it in a different way. So it's going to, in effect, we're dividing, right, by doing it that way. So let's see how this works out. Let's actually distribute this in and multiply these out. So to multiply the numerator, I need to do FOIL, right? So 2 times 4. Let me do this back in black. So 2 times 4, it's going to be 8. 2 times I is plus 2i. Then the inner, I have 5i times 4 is 20i. And then 5i times I is plus 5i squared. Remember that the I squared is negative 1. Okay. And then in the denominator, I have 4 times 4, which is 16. I have 4 times I, which is 4, positive 4i. I have negative I times 4, which is negative 4i. See how those are going to cancel. And I have negative I times positive I, which is negative I squared. But again, remember I squared is negative 1. So if we simplify this, right, I have, let me just write it one more time. I have 8 plus 2i plus 20i. And then positive 5 times negative 1 is minus 5. In the bottom, I have 16 plus 4i minus 4i. And then negative I squared is negative. It's basically negative 1 times negative 1, which is plus 1. So if I combine like terms now, in the numerator, right, I can combine the real part. So 8 minus 5 is going to be 3. And then the imaginary parts, 2i plus 20i is 22i. In the denominator, notice there's no more i's, right? The 4i and negative 4i are gone, and I just have 16 plus 1, which is 17. So that's the answer, but usually you write it like this. I'm going to take each piece and put it over 17, right? So this is 3 over 17 plus 22 over 17 times I. And I write it like that because now it has the form like something A plus something times I, right? It has that form A plus BI. Okay, so I just want to do that one example, but that's how you divide complex numbers. You multiply the numerator and denominator by the complex conjugate of the denominator. Okay, the last thing I want to talk about is just simplifying powers of I itself. So let's look at a couple of these. Let's say I start with I raised to the 0. Well, this follows the same rule as anything raised to the 0 power, as long as it's not 0 itself, is equal by definition to 1. So this is equal to 1. If I do I to the 1 power, that's equal to itself, right? That's just equal to I. Anything raised to the 1 power is itself. If I do I squared, notice by definition, right, we define that to be negative 1. If I do I cubed, you can think of this as I times I squared, right, using your rules of exponents. It will follow all the original rules of exponents. But I squared is negative 1, so this is like negative I. If I do I to the 4th, this is like I squared times I squared, but that's negative 1 times negative 1, which is positive 1. If I do I to the 5th, this is like I times I to the 4th. So this will be positive 1 times I, which is I. If I do I to the 6th, I'm going to get, I'll write it as I squared times I to the 4th. Well, we know I to the 4th is 1. I squared is negative 1, so this is going to be negative 1. It turns out I to the 7th is going to be negative I. And then I to the 8th is going to be 1 again. So notice here that the pattern repeats, right? After every 4, it repeats. So the pattern, I'll write that out here. The pattern repeats for every 4 powers of I. So that means when I take I and I raise it to any power, I'll just use like an asterisk to represent the power there, that is equal. So that I raised to some power is always either going to be 1, I, negative 1, or negative I, right? Because the powers repeat. So to figure out which, what we have to do is we basically divide the exponent by 4 and just look at the remainder. Okay, so basically what we're saying is if the remainder, here, I'll make a little table here. If we divide the exponent by 4 and we look at the remainder, and if the remainder has a value of 0, then I raised to that exponent that has a remainder of 0 is going to have a value of 1. Okay, and we saw that here, right? When we did I to the 0, we got 1. 0 divided by 4, the remainder is 0, so the answer is going to be 1. If I do I to the 4th, right? Okay, again, I apologize. I'm having problems with the iPad and it just keeps going blank on me. So let me try this one more time. So to figure out whether our answer is going to be 1, I, -1, or -I, we need to just look at the remainder when we divide the original exponent by 4. Okay, so I'll write that here. So to figure out which value we're going to use, either the 1, I, -1, or -I, we divide the original exponent by 4 and just look at the remainder. Okay, then if the remainder, I'll make a little table here. So if the remainder, when we divide the original exponent by 4, is a 0, then our answer is going to be a 1. If the remainder is a 1, the answer is going to be I. If the remainder is a 2, the answer will be a -1. And if the remainder is a 3, then the answer will be -I. And then it's because we're dividing by 4, it'll only be one of those 4 values, right? It'll be 0, 1, 2, or 3. So, and you can see that here from the original, right? I to the 0 is 1, I to the 1 is 1, I to the 2 is -1, I to the 3 is -I. Then, if the original exponent were 4, when we divide that by 4 and we look at the remainder, we're going to get 0 again, and the answer is 1. And we know that I to the 4th is equal to 1. If I take, say, 5 and divide by 4 and look at the remainder is 1. So the answer is going to be I, and I know I to the 5, we worked it out, is equal to I to the 5th is equal to I. And so on and so forth. So all we need to look at is the remainder of the original exponent divided by 4. So for instance, let's do a couple of problems here. So if I have I to the 18th, right? All I have to do is take the original exponent, 18, divide by 4. If I do that, right, I'm going to get 4, this is 16, remainder's 2, right? So the remainder is 2. So what does that mean? Well, if I look at my table now, if the remainder is 2, my value is going to be -1. So that tells me that I to the 18th is equal to -1. And I'm done. I just have to look at the remainder. What about this one? I kind of wrote into the space here, but so I to the 71. So I take my original exponent, 71, divide by 4. This is going to go in once, 31, and then 4 goes into 31, I guess, 7 times? So it'll give me 28. So the remainder is 3. So if the remainder is 3, then I go to this table here. If the remainder is 3, I know my answer, my value is going to be -I. So that means that the original problem, I to the 71, simplifies to just -I. Okay, so all you have to do is look at the remainder. Now, there are other ways of doing this. This is the easiest way. Just divide the original exponent by 4, look at the remainder. We could just use exponent rules, right? Like, let me just show you this quickly, and that'll be it for this section. We could use the exponent rules. Right? So if I have I to the 18th, I can write that as I squared, because we know I squared is -1, right? We know that, raised to the 9th power, right? This is like the rule if I have x to the a raised to the b, then I multiply the exponents. So I'm going backwards. I'm thinking of 18 as 2 times 9, so I'm writing as I squared raised to the 9th. Well, I squared, again, we know is -1. And if I raise -1 to an odd power, like -1 times -1 times -1 times -1, I'm going to get -1, right? So this tells you that I to the 18th equals -1. So we can get it using exponent rules, but it was much quicker to just look at the remainder, right? Divide by 4 and look at that remainder. I could also do the other one this way, right? Here's the trick to it. I would write I to the 71 using exponent rules first as I to the 70th times I to the 1. Right? Remember, if you, here's the other rule we need, right? If we have x to the a times x to the b, the rule is you keep the base x and you add the exponents. So I'm just going backwards. I'm saying 71 is like 70 plus 1. So I to the 71 must be the same thing as I to the 70th times I to the 1. Then I rewrite the one with the even exponent as I squared raised to, well, 2 times what will give me 70? 35. Times, and I still have an I here, I to the 1, which is I. But I squared is -1. And then -1 raised to an odd power is going to be -1. And I still have an I there. So this simplifies to -I. Right? It's a lot more work to use the exponent rules. It's just much quicker. What we got before is we took the original 71, divided by 4, looked at the remainder, which is 3, and then based on this table here, we knew that the answer had to be -I. So we had -I. Right? You'll get the same answer. It's just more work to use the exponent rules. Okay, hopefully that this recording will fully work now. Next, we're going to look at quadratic equations, section 2.5. Thanks.